Our galaxy is filled with strange planets. Now, this should not surprise anyone. You just need to look at our own solar system to get a sense of the variety that exists. Rocky planets, gas giants, boiling surfaces, icy worlds. Some planets with rings, others with moons. Some with storms the size of entire smaller planets. But those pale in comparison to the marvels that exist once you start to look further afield. To date, NASA has confirmed the existence of more than 6,000 exoplanets in the Milky Way, and while many of them seem to follow the mold of what we would see in our solar system, others, to say the least, seem truly bizarre. Worlds with multiple suns in their skies, worlds with rain made of molten iron, worlds with rings the size of Venus's orbit, worlds larger or hotter than stars. But out of all this, what are the strangest planets we've discovered? What are the marvels our galaxy has in store for us? And what further wonders may still be out there? I'm Alex McColgan and you're watching Astrum. Join me today in this supercut as we take a look at the Milky Way's strangest exoplanets. When it comes to planets, many things can make them strange. For instance, sometimes strangeness is not found in the planet itself, but how it moves around its star. While we are used to some large or small orbits in our solar system, how long or short can a year actually get? Let's start off close to home. Mercury has a pretty short year, only 88 Earth days, which is the shortest orbit that we know of in our solar system. And very interestingly, due to the way Mercury rotates, one Mercurian day is twice as long as its year. Yes, there's exactly 2 years in its solar day. So should anyone ever live on Mercury, you would have to switch around your way of thinking when it comes to describing a shorter reference of time. But it's kind of cheating to say a year on Mercury takes half a day, when it still takes 88 Earth days. So let's keep to Earth timescales as the point of reference. Outside of the solar system, most exoplanets that we know of have really short years, and that's because of the way we detect the majority of exoplanets. There are observatories that look closely at thousands of stars at the same time, looking to see if an orbiting exoplanet passes in front of its parent star, causing the star to dim ever so slightly from our perspective. In order for us to confirm that the dip in brightness is caused by an exoplanet, we need to see a pattern of dips in regular intervals. So if an exoplanet does transit a star, but it takes 2 Earth years before it transits again, then we would need to be constantly monitoring the star for many years before we can confirm that the dips in the star's brightness are caused by an exoplanet. On the other hand, exoplanets with really short years, like a few days or weeks long, can be confirmed as exoplanets very quickly. This means that most exoplanets that we know of only take a few days to orbit. The famous TRAPPIST system exoplanets all orbit their parent star within 1 month. The closest planet to the star only takes 1.5 days. So, out of all these thousands of exoplanets that we have discovered so far, which one has the shortest year? Incredibly, there's a pulsar out there which has a planet, although it could also potentially be the core of another collapsed star, which orbits around the pulsar in only 48 minutes and 58.5 seconds. How can this happen? Well, not only is the orbiting object extremely close to the pulsar, but it is moving very fast. A neutron star is also very small, at most only around 30 kilometers across, yet it is incredibly massive. So much so that its gravity even bends light around it. A fast-moving object can stay in orbit because the neutron star's gravity is strong enough to keep it there. Although, you may say this is cheating again, a pulsar isn't really a star, more like a star remnant. So what about a main sequence star? In this case, the shortest year that we know of goes to K2137b, a planet that's year lasts only 4.31 hours. Because it is orbiting a main sequence star, The Earth-sized exoplanet is surely orbiting within the star's atmosphere and will eventually either be ripped apart by tidal forces or fall into the star completely as atmospheric drag slows it down. On the other end of the scale, the longest year that we know of belonging to a planetary mass object is this beautifully named planet. This Jupiter-type object's year lasts roughly 1 million years. Still, for some planets, talking about how long it takes for them to orbit their star doesn't make sense at all. After all, some orbit more than one. In our solar system, we like to keep things simple. Just the one star found in the center with everything else orbiting around it, as is the case for most planetary systems found in the universe. However, there are some planetary systems out there where things get a bit more complicated, specifically multi-star systems, where there are 2 or more stars that orbit each other. In such configurations, what happens to any planets orbiting them? In fact, can planets orbit them at all with the gravitational tugs from different directions? To answer the latter question, the simple answer is yes, planets can orbit in such situations. Although, to answer the former question, there is no one-answer-fits-all rule about how a planetary system in a multi-star system might look. What we can do, however, is explore some of the possibilities out there. But before we look at planets, it would be good to understand how multi-star systems work. For the most part, stable star systems have organized themselves into hierarchical systems. This is due to the proximity in which they formed with each other, which we will touch on a little later. Binary star systems are generally simple enough. Binary stars orbit around a barycenter, or in other words, their center of mass. If the masses of these 2 stars are similar, then nearly symmetrical elliptical orbits are often seen. Although there can be occasions where they orbit in circles, in a similar fashion to Pluto and Charon. In the case that one object is more massive than the other, then the more massive object's orbit doesn't take it as far out compared to the less massive object. Beyond binary systems, you can have 3, 4, 5, 6, 7 or more stars in the same system, and as you will see, there is a structure within these systems to keep them stable. In the case of 3 stars, you'll have 2 stars orbiting each other in a binary configuration, with the third orbiting around a barycenter with the other 2. This keeps the system stable, because if 3 stars had their orbits cross, one would certainly get ejected from the system at some point. In a 3-star system, 2 of the stars are contained in their own enclosed little system, acting as 1 star in the grand scheme of the whole system itself. We group this binary configuration into a tier, with that tier acting together in its association with the single star. In a way, once you have grouped the binary configuration in the system, this upper tier now acts like a 2-star system again, with the 2 stars and the 1 star orbiting each other. In the case of 4 stars, you'll either have 2 binary configurations orbiting around a barycenter, or 1 binary system orbiting a barycenter with a 3rd star, and all 3 of those stars orbiting around a barycenter with a 4th star. From here on is where the hierarchical system really comes in handy. With a chart like this, you can easily see how the system works. In the 2 binary configuration case, you have the 2 binaries orbiting the system's center of mass. In the single binary and 2 single stars configuration, you'll add another lower tier in the configuration. You have the binary here, which orbits this 3rd star, and all 3 of these stars are orbiting together with the 4th star. If there are more stars in the system, say 5, you can have an array of configurations, with various binaries or single stars on a variety of tiers. Yet with this chart, you can easily see where the mass lies. You can do the same for systems with 6, 7 or more stars, but anything above 7 is exceptionally rare and probably won't remain stable, although maybe there are examples somewhere in the universe where it exists. So let's add planets into the mix. Could there be a planet out there with 7 suns in its sky? Well, yes. Let's have a look at this hypothetical 7-star system again. By here, there are 3 stars in a configuration, 2 in a binary configuration and a single star. We see that the single star has planets that specifically only orbit that star. They have 1 sun. Beyond that, there are planets that orbit both that star and its binary companions. These planets could be said to have 3 suns, as they are orbiting 3 stars. Going to the top tier, there is a planet here that orbits the entire system. This planet could be said to have 7 suns. Let's see what that looks like outside this graph. Interestingly, in a 7-star system, from this distance it only looks like the orbit of a binary. That's because each set of stars is found in one of these 2 points. Here is the planet with 7 suns. Its orbit takes it so far out that these stars aren't very bright in the sky, so even though it has 7 suns, they don't really provide much in the way of warmth or light. Zooming in on the set containing 3 stars, we see the planets which orbit all 3 of these stars. These stars would appear much larger in this planet sky compared to the planet sky that was orbiting all 7. In this example, the 2 in the binary configuration appear almost too close together to distinguish, with the single star clearly separate. The other 4 stars that are part of the other set in the system are dim in the sky. They are very far away, and again don't provide much in the way of light or warmth, meaning there is a clear day and night on these planets. Interestingly though, this other set of stars would get marginally brighter and dimmer during their orbits, and the distance between their system's orbits would get more noticeable as they get closer. Lastly, let's look at a planet orbiting just the 1 star in this system. It orbits closely to the star and is tidally locked, although the night side would be disrupted by the binary configuration this star orbits with, as the planet's orbit can take it between the single star and the binary stars. The binaries orbit together closely, and so wouldn't easily be distinguished in the sky without a filter. Again, the other set of stars in the system would be dim and appear far away. This may make you wonder how many systems out there have more than 1 star. Are we unusual, or is it the trend that there is only 1 star per system? Well, if you look up into a clear night sky, it may surprise you to know that most of these stars are binaries. The brightest star in the sky, Sirius, is a binary. Alpha Centauri, the closest star to us, is a binary, or maybe even a trinary if you include Proxima. Polaris, the North Star, is also a binary. So for the longest time, astronomers thought that we were the unusual ones. However, it's coming to light with the improvements in technology that this is not the case, and that most star systems only contain 1 star. Perhaps the reason why the brightest stars in our sky are binaries is because they are giving off twice the light. Single stars are just generally dimmer and harder to see in comparison. It doesn't help either that 85% of all stars in existence are red dwarfs, and it seems that only about 25% of them have companions. In fact, it's interesting that binaries occur much more frequently with the really massive stars, the blue and white giants. This could be because of how these stars formed. Red dwarfs weren't pumped with as much material as they were forming, hence why they never attained the mass of a blue giant. In an environment where forming a blue giant is possible, however, models suggest that several stars could form at the same time. At first, these systems would be chaotic. The stars would be ejected until order could be found. The ones that remained and survived were the ones that ended up absorbing the most interstellar medium, thus becoming the most massive of stars. The interstellar medium that ended up caught in protoplanetary disks around these stars later formed planets. The first planet we ever discovered with more than 1 sun in its sky was Kepler 16b, spotted by NASA's Kepler Space Telescope in 2011. At the time, it became known as the Tatooine planet. However, Kepler 16b is no desert world, but is actually a gas giant around 0.3 times the mass of Jupiter. tracing its orbit around its star has fascinated scientists who are trying to unravel the three-body problem, the complicated mathematics that traces how three orbiting bodies interact with each other. Since then, a handful of other Tatooine planets with their multiple stars in their sky have been discovered, indicating that they are not uncommon in our universe. After all, more than half of all stars in our galaxy have at least one partner. But what would it be like to live on a planet with two suns in the sky? Or, to help us visualize the point, how much would having a second star impact us here on Earth? How hot would Earth get? What would the day and night cycle be like? Would it be possible for life as we know it to survive in a multi-star system? Well, it depends. Let's keep our sun as it is, and only make the second star the variable in this thought experiment. As we know, stars come in all sizes, from small, cool and dim red dwarfs, all the way up to large, hot and bright blue supergiants. In a binary star system, the stars orbit around the system's barycenter, or the center of mass. Depending on the mass of the stars and the distances between them, you'll have differences in how these orbits look. For similarly sized stars, the orbit could look circular in nature, or in an ellipse. On the other hand, the bigger discrepancy there is between the star's masses, the closer the barycenter will be to the more massive star. Let's say we plonk a red dwarf, which is the smallest star type, in a close orbit around our sun. Even though a red dwarf can be as little as 7.5% the mass of our sun, it's already going to have a big impact on us. From our perspective, the star would look like it orbits the sun, meaning there would be times when it transits in front of the sun and other times where it is eclipsed by the sun. Our year would be shorter if we stay 1 astronomical unit from the star's barycenter. Because of the increase in mass and gravity of the system from the extra star, Earth's velocity would have to be faster in order to not be pulled into the stars. Either that, or its orbit would have to be slightly further out if we want to maintain our current velocity. The increase in temperature from the star would be noticeable too, definitely making it unbearable for humans. But exactly how hot would depend on a variety of factors, like a runaway greenhouse effect, the heat of the star, and more. But let's say we place Earth's orbit in such a location that we can survive. Seasons would still be massively impacted, as the tilt of the planet would be secondary to the distance to the second star. When the second star is as far away as possible, and a hemisphere on Earth was also experiencing winter, it would get extremely cold. On the other hand, combine a summer with the second star passing as closely as possible, and it will be incredibly hot. Additionally, a curious phenomenon with red dwarfs is that they also produce huge flares, much larger than the ones our sun produces. They would easily knock satellites offline on a regular basis, and Earth would have spectacular aurora. Our power grid as it stands would also be under serious threat from these stellar flares, as they would act like hemisphere-wide EMP bombs. The interactions with the second star could well make our sun more active too, meaning it too may produce more flares. So even with the smallest type of star, our habitability on Earth would be under serious threat. Increase the mass of the second star, and you'll start to get additional problems, like increased UV radiation, making going outside more and more dangerous. You'll also have two shadows a lot of the time. Once you turn the second star into something like a blue supergiant, there really won't be a place in the solar system where there is even a hope of habitability. Blue supergiants can be many times the mass of our sun, the theoretical limit being 150 solar masses, although some argue this should be higher. Their volume is also big. They make the sun look absolutely puny in comparison. They can be millions of times more luminous than our sun too, with devastating stellar winds, enough to rip our atmosphere off over a relatively short time frame. Larger again are yellow supergiants, and then red supergiants. While not as massive or as luminous as blue supergiants, red supergiants are the largest stars in existence. If you plop the largest known of these stars directly into the center of our solar system, not only would they easily encompass Earth, but everything up until Saturn. That's 10 billion times the volume of our Sun. However, there is a scenario where we could be in a binary star system with a supergiant and still be on a habitable planet. You see, binary stars can orbit very far apart, taking thousands of years to complete one orbit. The most extreme cases can see a binary star system with a separation of over a light year, and what can happen is that planetary systems will form around each of these stars separately, meaning that if Earth was in one of these planetary systems, it would only have the one parent star, even if that star was part of a binary. The second star would be easily visible in the night sky, but may not make much of an impact during the day, depending on its luminosity. Stellar winds from the other star would have very little impact on Earth, as our Sun's powerful magnetic field would redirect most of it away. The big problem with a supergiant on your doorstep is that it is a ticking time bomb. Supergiants tend to be on the verge of erupting in a supernova. A supernova going off only 1 light year away would be catastrophic, probably sterilizing the entire planet as radiation from the shockwave passes over. And that's not to mention the gamma ray burst from the resulting neutron star. In fact, a recent study has suggested that being within 50 light years of a supernova going off would be close enough to be catastrophic in nature. However, the good news is that we don't know of a star capable of erupting in a supernova within 100 light years. Going back to the single parent star binary star configuration, on Earth with a single sun, we have a set day and night cycle. However, should we have a second sun outside of our orbit, but still pretty close to us, it's going to mess with our day and night cycle pretty badly. There would only be tiny parts of the year where you would get a proper day and night cycle, and as the year progresses, you'd get less and less of a night, until at one point you'd have no night at all. So, living on a planet with more than one sun is no walk in the park. No wonder Luke wanted to leave Tatooine. Still, they are likely more hospitable than conditions on our next category of strange planets: rogue planets. Rogue planets are one of the great mysteries left in the universe. They are planetary-sized objects that are not gravitationally bound to a star. We don't fully understand how they formed. Perhaps they were born in a planetary system but got ejected during the system's turbulent beginnings. Following that thought, perhaps our own solar system also had additional planets at the beginning before they were cast away to forever roam the galaxy alone. Rogue planets could also be protostars that simply failed to absorb the mass needed to become a star or even a brown dwarf. We expect there to be billions to trillions of them out there in just our galaxy alone. Although, because they are hard to detect, this really is an educated guess at best. However, since the turn of the century, we have started to detect a few of these mysterious objects. How can that be when there are no stars lighting them up, and since they don't emit their own light? If they are pitch black, how do we have any hope of detecting them at all? Well, this is where a very interesting detection technique comes in, called gravitational microlensing. On this channel, we have explored various exoplanet hunting techniques in the past, mainly the radial velocity method and the earlier mentioned transit method. The radial velocity method measures the wobble of a star caused by the gravity of orbiting exoplanets. As we talked about earlier, the transit method measures the brightness of a star over a long period of time and looks for the dips in the star's brightness when an exoplanet passes in front of it. However, these methods are only useful for detecting exoplanets around stars, and generally, these exoplanets tend to be large and have very close orbits. The gravitational microlensing method is an exciting method because not only can it find exoplanets much further away from their host stars, but these planets can also be as small as Mars, or possibly even smaller than that, and still be detected. Additionally, rogue planets with no star at all can be detected with this method. Sounds almost too good to be true, but there is one catch. So how does it work? Gravitational lensing is a well-known phenomenon in astronomy and has been used for years to detect some of the most distant galaxies that we know of. Einstein predicted this phenomenon back in 1936, and with the development of telescope technology, it has been confirmed by observation. Basically, the further away a light source is from us, the dimmer it becomes thanks to the inverse square law. The reason objects get dimmer with distance is that photons spread out as they travel, meaning the further away you are from the object, the fewer photons that reach your eyes. However, when there is a body with a large amount of mass, like a galaxy or galaxy cluster, the mass of the object warps the curvature of space-time depending on how massive it is. Light follows the curvature of space-time, meaning that if light emitted by a distant object travels past a massive object, the light photons that would have otherwise gone off in these directions bend back around thanks to the object's gravity, making the background object appear brighter to an observer here than it otherwise would have done, as more light photons are reaching them now. Gravitational lensing is very obvious when we look at the biggest types of objects, galaxy clusters, because these objects warp spacetime the most. This means that if we are aligned just right with a galaxy cluster and a distant galaxy, the distant galaxy would appear much brighter. The light from the distant galaxy bending around the nearer galaxy would also actually make the galaxy appear stretched, sometimes into the form of a ring. You may have seen these Hubble images before, where distant galaxies appear totally distorted thanks to this gravitational lensing effect. And here is a CGI example of what you are seeing, which may help you understand why this happens. Now, as I mentioned, more recently the use of gravitational lensing has also been used to help astronomers detect exoplanets. Stars and planets are much less massive than galaxy clusters, but gravitational lensing still happens to a small degree. When a star transits in front of a distant star, the distant star will become brighter as its light follows the curvature in space-time around the foreground star. Additionally, should the foreground star have an exoplanet or exoplanets, the distant star will also get slightly brighter when these transit in front of the distant star too. This is the process of gravitational microlensing. This process is so accurate that small Earth or Mars-sized exoplanets can be detected, and potentially even large exomoons. Astronomers simply need to measure the little peaks in brightness to distinguish between the individual bodies orbiting the foreground star. Now, as I mentioned, there is a catch with this method, and that is that star transits are actually quite rare, because they really need to be aligned just right from our perspective, and the galaxy is simply huge. There's so much space in between stars. This is why, up until now, the transit method has had a far better success rate at detecting exoplanets, because exoplanets orbit and transit their stars a lot quicker than stars transit other stars. So, in order to spot these events, what we need is to observe a huge swath of sky in one go. Enter the Nancy Grace Roman Space Telescope, previously known as the W1st Observatory. This telescope, due to be launched no later than 2027, is comparable in size and will provide images with a sharpness similar to the Hubble Space Telescope, except the Roman Space Telescope will be equipped with a 228 megapixel camera and a 2.8 squared degree field of view, which is 100 times larger than Hubble. With this field of view, it will be able to keep track of a much larger section of the sky and monitor for microlensing events. How does this all fit in with rogue planets? Well, much like stars, rogue planets that transit in front of a distant star will also make that star slightly brighter. And if the Roman Space Telescope is looking at that section of the sky, it should be able to detect it. In fact, throughout its 5-year initial mission, Scientists hope that the Roman Space Telescope can give us a much better indication of how many rogue planets and Earth-sized exoplanets there are out there. Now, while it is possible that rogue planets are in any section of the sky, the Roman Space Telescope will focus its time looking towards the center of our galaxy. There are a lot more stars here, so transit should be more frequent, and this will increase the chances of spotting microlensing events. It is amazing to me that there are ways to detect these otherwise invisible objects that emit no light, and all you need to do is look at the brightness of a background star, and as a rogue planet passes in front of it, the gravitational microlensing event will reveal key details about the rogue planet, like its mass. So, have we detected any rogue planets this way at all? As it happens, yes we have. There are a few ground-based programs on the hunt for rogue planets operating right now, like Ogle, Moa, and Supermacho. At present, they have found 22 rogue planet candidates in all, with the most exciting one being Ogle 2012 BLG 1323. If this rogue planet gets confirmed, it will be the smallest rogue planet discovered by some ways, being roughly the mass of Earth. How a body like this comes to be free floating in space, we don't really know yet. What might conditions be like on a rogue planet? The first fact to consider is that they would be incredibly dark places. No nearby star means that conditions there would be pitch black. You might think that this might mean that they would be extremely cold places too, but this might not actually be the case. No nearby star also means that there is no nearby source of atmosphere stripping solar winds, which might actually help a rogue planet to retain any atmosphere it started out with. A 1999 research paper suggested that a hydrogen-rich atmosphere around a rogue planet could actually allow it to trap in enough of its heat that it could sustain Earth-like oceans. Still, any life that wanted to live on such a planet would have to be more akin to our chemosynthetic species on Earth that survive next to deep sea vents, relying on the planet's molten core to provide heat and nutrients. Photosynthesis would obviously be a no-go on a rogue planet. Other than that, rogue planets could potentially come in all shapes and sizes. Any planet that was flung out of its home system would, by definition, be a rogue planet. They could be gas giants or rocky planets. So, the context of where a planet is can make it pretty strange. But what about the planet themselves? What are some of the weirdest, strangest phenomena we might encounter on an exoplanet? Well, let's step away from dark, chilly rogue planets to something at the other extreme. WASP-76b is an exoplanet discovered in 2013 as part of the Wide Angle Search for Planets program. Since its first discovery, it has fascinated scientists due to its unusual properties. ESO's Very Large Telescope recently found one special characteristic in particular. On this planet, temperatures are so hot that instead of water rain, it rains molten iron. How can this be? Exoplanets that are very close to their stars, with very small orbits, are the easiest to discover, because we can see a very clear pattern on the star's light curve over a short period of time. WASP-76b is one such planet. Plus, it is huge, way bigger than Jupiter, and combine this with the fact that it only takes 1.8 Earth days to make one orbit, it made it comparatively easy to detect. But detecting the presence of an exoplanet is one thing. How do astronomers know anything about its physical characteristics? Interestingly, the first thing astronomers do is find out the physical characteristics of the parent star, WASP-76. The distance to the star is determined, and then the star is classified based on its brightness and color. Knowing the distance helps us determine how bright it is, and we measure its color simply by observing it, which helps us determine how hot it is. If the star is on the main sequence, then this chart also helps us know the radius and mass of the star, as they all tend to follow a pattern. Once we have that information, we can determine the characteristics of the orbiting planet itself.
Knowing the mass and radius of the star means we can measure the mass of the orbiting planet using some clever equations based on the law of universal gravitation. As it happens, WASP 76b is a super Jupiter, way bigger than our Jupiter. That means that although it is massive, this mass is spread out across a large volume, likely making it a gas giant. Orbiting this close to the star means the planet is probably tidally locked. Only one side faces the star at any given time. Also, due to the proximity of the planet, it orbits within the star's atmosphere, the physics of which we really don't understand yet. However, the star-facing side will be extremely hot, estimated to be around 2,400 degrees Celsius, easily hot enough to vaporize metals. Models go on to suggest the night side is about 1,500 degrees Celsius, still blisteringly hot, but much cooler. To find out what WASP 76b is made of though, we need to go back to the light curve of the transit. Scientists look for differences in the light when the planet passes in front of the star, as light from the star will shine through the planet's atmosphere. Certain atoms block certain wavelengths of light, so any reduced wavelengths help us know what is in the atmosphere. This is known as spectroscopy. For WASP 76b, the biggest surprise that scientists detected was an abundance of iron in the atmosphere. Based on what we know about the planet so far, it seems like iron exposed to the day side of the planet is vaporized, where it is transported through strong wind processes to the terminator line between the day and the night side of the planet. Here, the temperature is low enough for the iron to start to cool and condense, producing iron raindrops which fall deep into the atmosphere. By the time the wind has reached the morning side of the planet, iron can no longer be detected. This remarkable measurement, taken by the Espresso instrument on ESO's Very Large Telescope, is the first time variations have been spotted like this on an ultra-hot gas giant, although it probably won't be the last time.
Planets hot enough that they rain molten iron are certainly hot places to be. But they are not the hottest exoplanet we've seen. So, how hot can a planet get? Nestled in a tight orbit only 5 million kilometers from its parent star, roughly 10 times closer than Mercury orbits our Sun, sits a planet that is a raging inferno. Kelt 9 is a mercilessly hot star. At 9,700 degrees Celsius, is almost twice the temperature of our own Sun. The lone planet that orbits it, known as Kelt 9b, is a gas giant almost twice Jupiter's size and 3 times its mass. And orbiting that close to such a blaze, its daytime temperature surpasses that of some stars. Kelt 9b was recorded to have a temperature of 4,300 degrees Celsius, making it hotter than your average red dwarf star. Unsurprisingly, its hydrogen atmosphere is boiling off into space, but is then being dragged back into its star at a predicted rate of 100,000 tons of hydrogen per second. In time, all of Kelt 9b's atmosphere will be drained away, leaving the planet's core exposed to that blistering heat. Kelt 9b's core will either be eaten then, or the planet as a whole will be consumed when the star Kelt 9 expands in 300 million years. In the meantime, the surface of Kelt 9b is hot. Hot enough that molecules on its surface break down, ripped apart by all that energy. All in all, it would not be a nice place to live. On the note of planets hotter than stars, is it possible for planets to exist that are larger than their parent stars too?
If you were to imagine a star system, you'd probably think of a giant star being orbited by smaller planets. And generally speaking, this is the standard for star systems across the universe. However, solar systems come in many shapes and sizes. Could it be that there are planets out there that are bigger than the star they are orbiting? And leading on from that, how big can planets get? What's the biggest one that we know of? First of all, let's define one point. When we talk of big, what we are actually referring to is the volume of an object, not its mass. In order for a star to be a star, it has to be over a certain mass, namely 0.08 solar masses, or 8% of our Sun's mass. Below this threshold, the object is classified as a brown dwarf, because it didn't become massive enough for nuclear fusion to take place in its core. Lower masses than brown dwarfs are simply planets, asteroids, and dust. So the minimum mass of a star is 0.08 solar masses. Is there also an upper limit? Theoretically, the most amount of mass a star can attain is about 150 solar masses before models suggest it would lose its stability.
Although, interestingly enough, there are some stars in existence that seemingly contradict that theory, with masses that are estimated to be around 300 solar masses.
Regardless, just because a star is massive doesn't mean that it's big. Some of the densest stars in existence, neutron stars, are 1 to 2 solar masses and can be only 30 kilometers across. Imagine fitting the vast mass of our star, an object so huge that it dwarfs Jupiter considerably, let alone us, and squeeze up to 2 of these in a space the size of a large city. While these stars are tiny volume-wise, they easily have enough mass to host a grand solar system that could stretch far beyond our own. We have discovered exoplanets around neutron stars. However, due to the detection method used to discover them, we can only really define their mass, not their radius. It would make sense though that these planets are many times bigger than the tiny star, as we have asteroids in our solar system which can be hundreds of kilometers across, let alone planets thousands of kilometers across. White dwarfs are another example of tiny stars that likely have larger planets orbiting them. White dwarfs are the remnants of red giant stars that weren't massive enough to become neutron stars in a supernova explosion when they reached the end of their lives. Instead, they shed their outer layers in a planetary nebula, leaving behind the core of the star, or what is known as a white dwarf. Nuclear fusion does not take place in a white dwarf, meaning their luminosity comes solely from stored thermal radiation. This makes them quite dim stars, and they only get dimmer over time. Planets that would have survived the star's evolution from main sequence to red giant to white dwarf could well be larger than the small remnant white dwarf, which is typically the radius of Earth. There came a confirmation of such a planetary system in 2020 thanks to the TESS Observatory, an exoplanet known as WD 1856b. What's remarkable about this system is that the planet orbits the white dwarf relatively closely, meaning it survived the star going through its red giant phase. The red giant phase would have easily enveloped where the planet now resides, so this means the planet must have fallen or scattered into this orbit after the event, perhaps thanks to the gravitational influences of the star's other undiscovered planets, or even from nearby stars that the white dwarf is gravitationally bound to. In any case, it's an incredible system indeed. When it comes to main sequence stars, planets larger than them are tricky to find too. We believe that main sequence stars make up the majority of stars in the universe. These can be very big objects, as internal pressure from the reactions in the core keeps the radius large. We'd have to look for stars right around the dividing line between brown dwarfs and red dwarfs to find a main sequence star small enough to host a larger planet. Remember, the difference between a brown dwarf and a main sequence star is whether nuclear fusion takes place in the star's core, which we believe happens above 0.08 solar masses. And we also believe the dividing line between a planet and a brown dwarf is around 13 Jupiter masses. So, one of our best bets to find a tiny star with a large planet is looking around the red dwarf VHS 1256-1257. Its exoplanet is one of the few exoplanets to be discovered using direct imaging. Its host star is dim enough, the exoplanet is far enough away from the star, and big enough to be seen simply by using a powerful telescope. Unfortunately though, this means that while the mass of the exoplanet has been determined, we can't know of its radius for sure. However, this is one of the most likely candidates that we know of. Also, because of the margins of error involved, it could well be that either or both objects are brown dwarfs, meaning we can't say if this is truly a star and planet system. So while we don't have definitive proof of a planet being bigger than its host star, we have found some promising candidates, and there's almost certainly cases out there that we haven't found yet. Some of the smallest stars out there have a radius of roughly 70,000 kilometers. Some of the biggest planets out there can be double or triple that. Which leads on to the final question I wanted to cover here. What is the biggest exoplanet that we know of?
Unfortunately, it is not clear-cut. One possible answer is GQ Lupi b. It is another directly imaged exoplanet, which again means we don't have a good grasp on its physical characteristics. From the margins of error involved, it could be a brown dwarf, but it's probably the largest exoplanet that we know of. Scientists have estimated its radius to be 3 times the size of Jupiter, but again, there are margins of error involved. Other contenders to this throne would be DH Tauri b and ROX 42BB. We've looked at a lot of exoplanets in the course of this video today. Some of the hottest, the coldest, planets with multiple stars, planets with none, the fastest orbits, and the longest. But I want to finish with an exoplanet that would be visually stunning if its existence were to be confirmed. J1407b, touted as the first exoplanet discovered with a ring system like Saturn. Sometimes it is surprisingly tricky to spot ring systems around planets. It was only in 1977 that Uranus's rings were discovered. Jupiter's rings were only spotted in 1979 when they were imaged by the passing Voyager probe, and Neptune's rings weren't seen until the early 1980s. This is because, in the absence of nearby probes to photograph them, rings are usually discovered via either the transit method or stellar occultation, when they pass in front of a near or distant star, causing the light reaching us to momentarily dim. Usually you have to be looking carefully. However, not so with J1407b. When planets like Jupiter pass in front of its neighboring star, they can sometimes block as little as 1% of the star's light. Their rings, much less than that. When J1407b passed in front of its star, it blocked an incredible 95% of the star's light. Why was this? In 2012, researchers who noticed this phenomenon in the SuperWASP data came up with the answer. J1407b had rings, massive ones. By evaluating the dips in the light, astronomers were able to detect a complex ring structure around the planet that covers more than 40,000 times the area of Saturn's rings. For point of reference, this represented rings as large as the orbit of Venus around our Sun. Just like with Saturn, at least one small moon had begun to form within the rings, creating gaps and indicating that the planet's rings will not last forever. However, right now, if this interpretation of the data is correct, they would be a sight to behold. Sadly, there is a reason to look at this answer with suspicion. J1407b supposedly travels around a star once every 10 years, but since that initial eclipse, no equivalent dimming events have been cited. Scientists are attempting to explain whether this means J1407b was actually just a one-off event, a free-floating brown dwarf with its own protoplanetary disk that just so happened to pass by the star by coincidence, or whether J1407b could still be an orbiting planet with massive rings, albeit ones that are much thinner than first anticipated. So there we have it. Some of the strangest exoplanets out there. Are there any you feel I've missed? What were your favorites? Let me know in the comments below. Astrum isn't just made possible with sponsors and ads. It thrives because of our Patreons. Please join us so we can keep creating more and better videos and making space accessible for everyone. Patreon is where viewers become part of what keeps Astrum running, the place where people who love space gather to make sure these videos keep coming. You'll get ad-free viewing, early access, and a closer connection to how the channel grows. We're building something steady and long-term, and every new member makes it stronger.